Hello, my students. Now to begin the adventure of electrochemistry. Electrochemistry will be our last full unit for our year of AP Chemistry. Electrochemistry, the term electro, remember thermochemistry was all about heat, therm. Well, electrochemistry involves electricity, specifically with two goals: getting a chemical reaction to do electrical work for us, or use electrical work to make a chemical reaction that is non-spontaneous be spontaneous. Electrochemistry, the study of the interchange of chemical and electrical energy. So actually we could begin at really the beginning. The very first individual who created a battery in the year 1800 was Alexander Volta. And what he actually did is fascinating. Through experimentation, he found that when he layered varying metals, and so for example, if we would take a penny, copper, alternating with a nickel, zinc, and then another layer of copper, and then zinc, and another layer of copper. Well, that didn't quite accomplish anything until Volta took a towel, soaked in a saltwater solution, and wove the towel in between the metal layers. So it'd be copper, the towel with the sodium chloride or any salt, zinc, the towel, copper, towel, zinc, towel, and so on. And when he would stack 30, 40 alternating pieces, and when he would touch both ends, he would get a zing. What he was feeling was an electrical shock. Just like when you rub your feet along the carpet and shock your brother or sister. You're building up electrons. He was causing electrons to flow. So, can we use a reaction that moves electrons and get those electrons to do work for us? We'll get back to Volta in a moment. We'll come back to some common examples when we talk about the fundamental achievement of a battery. All right, how does electrochemistry work? Electrochemistry works because it is based upon relying upon our understanding of oxidation reduction. So for example, if we take copper and react it with zinc nitrate, we should recognize a single replacement reaction. We then get copper nitrate and kick out the zinc. Now, this copper is in the solid state. This is a solution of zinc nitrate. A solution of copper nitrate will be created, and zinc to be our solid. If we do the net ionic reaction for this, copper solid plus zinc plus 2 ion, 2 nitrates, do we see that nitrates are our spectators? And please do not forget, ladies and gentlemen, that copper here is in its elemental form. This is neutral. This is an entirely different species than this copper ion. We know what metallic copper looks like, and we know what the copper ion looks like in solution. So what's going on here and is driving this reaction to happen is first this losing electrons. And remember, lose electrons, oxidation. So here's what is going through the oxidation. The zinc is gaining electrons. Gaining electrons, reduction. So copper is giving its electrons to zinc. So could it be that we tap into those electrons to get them to do work for us? So, if we would take a beaker and place into it zinc nitrate solution, and then a solid piece of copper, the reaction will occur. Copper will go into solution, and zinc will come out. But how do we tap in to those electrons? So an idea comes about, well, what if we would just move them far apart? So what if then we would take a beaker, put the piece of copper, take another beaker, put our solution of zinc and nitrate. Of course, we need 2 of these for every one of those to balance neutrality. And then put these into contact through a wire. Well, that's not going to accomplish anything because copper will give electrons when it becomes copper plus 2. But where's the copper plus 2 to go? And here, what can the zinc plus 2 grab onto when it creates elemental zinc? So the next step, could we maybe place the entire oxidation in one species and then the entire reduction in another species? So let's give that a try. What if we would have our beaker, put our copper, but have a solution of the copper plus 2. Now, of course, we'd need the nitrate there to make it electrically neutral. Then have another with the zinc ion. Now, of course, we'd need a couple nitrates to make that neutral, and the elemental zinc. And then put these into contact. Then, when the copper ion is created, it can go into solution. And there's a place for the zinc to collect upon. Well, if we, while the electrons are traveling through this wire, ask it to go through a light bulb. The light bulb would light for just a moment. Well, why? I keep emphasizing again and again and again that ions are needed to maintain electrical neutrality. Remember what we would do when we balance a oxidation reduction half reaction? We'd have the copper creating copper plus 2. One copper, we don't have oxygen or hydrogen to balance. So to balance neutrality, this has a positive 2 charge, 0 charge, we'd add 2 electrons. And then for zinc, we have 1 zinc, but we'd have to add 2 electrons to this side. Well, as copper is creating the copper plus 2, it's getting more and more and more and more positive. And as we're losing zinc plus 2 ion, this is becoming more negative. And this has to remain neutral, and that has to remain neutral. So the electrons will flow for a moment, but as soon as these become positive and negative, electrons stop flowing. So what can we do? Well, back to Volta. Why did the inner laying of the salt-soaked towel allow to success for the batteries? What we need is what is called a salt bridge. We need to take a towel or some kind of absorbent material, saturate it with a salt solution, so let's say sodium chloride, and then put it into contact with both solutions. So, if I'm going to get a little crazy, if I could soak a towel and then extend it into that solution and that solution, that's my salt bridge. And this salt bridge would contain, if I indeed use sodium chloride, sodium ions and chloride ions. Sodium ions and chloride ions. So, as the copper plus 2 is being created, for every copper plus 2, 2 chlorides will flow into solution, making it electrically neutral. We want to create the salt bridge out of a compound that will maintain electrical neutrality, however, will not react with anything within here. And as we are losing zinc, well then, 2 sodium ions come in, maintaining electrical neutrality. When the salt bridge is in place, this light bulb will continue to light. That is our very first exposure. We're going to come back and look at how can we use this reaction to get electrical work.